እንትኑን ሳይሆን የሚገቡትን ላስገባ ኮንትሮል ማኒፑሌሽኑ ጠፍቶኛል። ሪከርዱን ለማስጨመር ብቻ ነው። Okay, good afternoon to you. Today we are going to see zeros of a polynomial function. The previous week we have seen the two important theorems in a polynomial, the factor theorem and the remainder theorem. Actually, if you remember, the remainder theorem is mainly used when a given polynomial f of x divided by a linear polynomial x minus c. In that case, we have said that we set x minus c equal to 0 and solve for x, and the value of x is equal to c. So evaluating the given function f at c, it gives you the remainder obtained when that polynomial is divided by the linear polynomial x minus c. But this theorem has limitation, and its limitation is it cannot be used for polynomials when the degree is greater than 1. And the other limitation is it doesn't tell you anything about the quotient obtained when a given polynomial is divided by the linear polynomial. The second theorem we have seen is a special case of the remainder theorem, because in general, according to the remainder theorem, when f of x is divided by the linear polynomial x minus c, any constant number, positive, negative, or 0, can turn out as a remainder. But in the factor theorem, a linear polynomial x minus c is a factor of a given polynomial when the remainder is 0 or when f of c is equal to 0. So it is a specific case of the remainder theorem. Today we are going to see zeros of a polynomial function. Actually, you have seen the solution for linear and quadratic function in grade 9 mathematics. So these two functions, quadratic and linear, they are again a specific case of polynomial, because a linear polynomial is a degree 1 polynomial and a quadratic is a degree 2 polynomial. So zeros of a function means simply the values of x obtained by solving the equation f of x equal to 0. So zeros of a polynomial is nothing but a real number c. If f of c is equal to 0, then c is 0, the 0 of f. According to this definition, definition 1.2, which you can see from your screens, for a polynomial function f and a real number c, if f of c is equal to 0, then c is the 0 of f. If c is the 0 of f, indirectly it is implying that the remainder obtained when f of x is divided by x minus c is 0. That means by the factor theorem, x minus c is a factor of this polynomial. So these notes explains that if x minus c is a factor of f of x, then c is a 0 of f of x, or c is a 0 of f of x minus c is a factor of f of x. Okay, so let us see the first example. Find the zeros of each of the following functions. F of x is equal to x cubed minus 3x squared minus 10x plus 24. B, a degree 3 polynomial x cubed plus 10x squared minus 24x. H of x. Melody.
What?
Melody. Okay. A degree 4 polynomial is presented in C. Actually, there is no one general rule which we follow to find the zeros of a polynomial. There are actually two theorems that minimize the steps we need to go through to determine the zeros of a polynomial. These are presented by the rational root test theorem and location theorem. Here, let me ask you one question. The real number is the union of dash and dash numbers. What is the correct answer for this? A real number is the union of dash numbers and dash numbers.
Integers and rational numbers.
No, you have got half of the question correctly.
Whole numbers and rational numbers.
No, you have learned specifically real number is the union of this and this number in grade 9, I think unit
Rational
1.
numbers and irrational numbers.
Rational and rational number. So the union of, if real number is the union of rational and irrational numbers, rational root test theorem tells you how you can find the rational zeros of a polynomial, and location theorem tells you how you can locate the irrational zeros of a polynomial, because the zeros of a polynomial are real numbers. So if real numbers are the union of irrational and rational, for irrational zeros of a polynomial, we will consider location theorem, and for rational zeros, we will consider the rational root test theorem. I will go to the detail of these two theorems in our next meeting, but for the time being, now consider f of x. X cubed minus 3x squared minus 10x plus 24. In polynomials, when you are interested particularly in finding the zeros of that polynomial, if the leading coefficient of that polynomial is 1, simply consider the factors of the constant term. If this polynomial has a 0 and they can be obtained through some calculation, then those numbers will be among the list of numbers that are factors of the constant term. In this case, if all the zeros, actually a given polynomial, if it has a 0, it is always equal to its degree. That means f of x can have 3 different zeros, or any number of 0 less than 3, that is 2 zeros, or 1 0, or no 0. Actually, for odd degree polynomial, the answer is not 0. I will tell you this. I will tell you why this is so while we have a discussion about graph of a polynomial function. But in this case, as I said, at least this polynomial has one expected solution, or 0. So f of x is equal to 0. Now, to find the 0 of a polynomial, what you do is simply set the given function equal to 0. That means the expression x cubed minus 3x squared minus 10x plus 24 equal to 0. Now, if you list the factors of 24, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. These are the complete list of factors of 24. I know that most of you, when you are asked to list the factors of 24, directly you list only the positive factors of 24. But 24 has both negative and positive factors. So when you are listing factors in polynomial, you have to remember to put, or you have to, don't forget to put this sign plus or minus before every factor. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 24, I mean plus or minus 12, and plus or minus 24. This is the complete list of factors of 24. So if this polynomial has a 0, it must be 1 or 3 numbers from among this set. So for example, if you consider 2, the reason why we choose 2 is, I already tried numbers, some numbers, but when you make x equal to 2, because we are seeing this before you are actually introduced to the rational root test theorem and the location theorem. So choose x is equal to 2. What matters in finding the zeros of a polynomial, if its degree is 3, is only getting 1 0. I will tell you what to do after obtaining this 0. So when x is equal to 2, 2 cubed minus 3 times 2 square minus 10 times 2 plus 24. So 2 cubed is 8, minus 3 times 2 square is minus 12, minus 10 times 2 is minus 20. So minus 12 minus 20 minus 32. 8 plus 24, 32. So 32 minus 32, it is equal to 0. Now we have obtained 1 0. This 0 is 2. Here I mentioned that if c is a 0 of f of x, indirectly, it tells you that x minus c is a factor of this polynomial. Now we are about to start going through the division process, long division, dividing the given polynomial f of x by x minus c, in this case by x minus 2. Now we totally focus on the quotient, because this is a factor. When f of x is divided by x minus 2, the remainder is 0. So ignoring the remainder, we focus on the quotient obtained. So 2 is the 0 of f. To find the other zeros of f, divide f by x minus 2 and solve the equation by setting the quotient equal to 0. Now the quotient obtained is x squared minus x minus 12. The polynomial divided by this factor, it is equal to x squared minus x minus 12. Now, you know how to find the solution for a given quadratic equation. That is why I told you at the start of solving this problem, as far as determining the zeros of this polynomial is concerned, obtaining 1 0 matters. After obtaining that 0, you convert it to a factor then you divide that polynomial to that factor, then you have a quadratic expression as a quotient. So you set that equal to 0, then you can use the general quadratic formula or the factorization method to find the solution for that. That means x squared minus x minus 12 equal to 0. From among the two methods, we usually or we often used to determine the solution of a quadratic equation, one is the factorization method. According to the factorization method, actually the factorization method is used when all the coefficients in this quadratic equation are integers. Now the coefficient of x squared is 1, the coefficient of x is minus 1, and the constant term is minus 12, so it is possible to apply the factorization method. Find two integers, their product is minus 12 and their sum is minus x. So using those two integers, the middle term in this quadratic equation will be substituted by those selected integers. These integers are minus 4 and 3. Minus 4 times 3 is minus 12. Minus 4 plus 3 is minus 1. So the middle term is x squared minus 4x plus 3x minus 12. Now we have the total number of terms in this quadratic equation becomes 4. So consider 2 at a time and factorize. So x squared and minus 4x. The GCF is x. X times x minus 4. And here the GCF of 3x and 12 is 3. 3 times x minus 4. So x minus 4 is common. If you take x minus 4 out, then you are left with x plus 3. So x minus 4 equal to 0 or x plus 3 equal to 0. And solving this, x is equal to 4 or x is equal to minus 3 is obtained. So the 3 zeros of this polynomial becomes minus 3, 2, and 4, which are all the factors of the constant term 24. Minus 3 is a factor of 24 because minus 3 times minus 8 is 24. 2 is a factor of 24 because 2 times 12 is 24. 4 is a factor of 24 because 4 times 6 is 24. So minus 3, 2, and 4 are the zeros of this polynomial. If you have any question, before we pass to the next example.
Mr.
Yes?
Minus 4x plus 3x እንዴት እናገኛለን?
እዚህኛው ጋር ማለት ነው። ይሄን ኳድራቲክ x ስኩዌር ማይነስ x ማይነስ 12 ኢኳል ቱ 0 የሚለውን ታውቃለህ። ጀነራል ኳድራቲክ ፎርሙላው ላይ ax ስኩዌር ፕላስ bx ፕላስ c ኢኳል ቱ 0 a different from 0 ከሆነ በኋላ ከዛ የኤክስን ሁለቱን ዋጋዎች ለመፈለግ ከምንጠቀምባቸው ሜትዶች አንደኛው ስቴት የሚያደርገው ሁለት ቁጥሮችንም እንፈልጋለን። where these two numbers are their product is a times c and their sum is equal to b. ድምራቸው ከኤክስ ኮኤፊሽንት ጋር እኩል የሆነ ፕሮዳክታቸው ደግሞ the coefficient of x squared and the constant term. So if you find these two integers, then you substitute the middle term bx using those two numbers. So in this case, we are interested in finding two numbers. The coefficient of x squared is 1. So 1 times any constant number is that constant number. So we find two integers, their product is minus 12 and their sum is minus 1. Product minus 12, sum minus 1. So among the different factors of 12, you list the factors of 12. So from among the list of factors of 12, then which of these factors, when multiplied together, gives minus 12 and their sum is minus 1? These two numbers are minus 4 and 3. Minus 4 times 3 is minus 12. Minus 4 plus 3 is minus 1. So the middle term minus x is substituted by minus 4x plus 3x. It doesn't change anything. What is minus 4x plus 3x, Robson? Minus 4x plus 3x.
Minus 1.
Minus x. So it doesn't affect the equation. X squared minus x minus 12 is originally given. Now the only difference between these two is in the original quadratic equation, the number of terms is 3. But in this case, the number of factors, the number of terms is 4. So if the number of terms is 4, Then by considering 2 at a time, we factorize. That is the next step. We take the GCF of these two, and it is x. X times x minus 4. Factorizing 3x minus 12, because 12 is divisible by 3, you take 3 out. Then you left with x minus 4. X minus 4 is common. If you take x minus 4 out, then you are left with x plus 3. So x minus 4 is equal to 3, or x plus 3 equal to 0. From x minus 4 equal to 0, the value of x is 4. And from x plus 3 equal to 0, the value of x is equal to minus 3. Now, is that clear?
Yes.
If not, you can use the general quadratic formula. The value of x is equal to minus b plus or minus the square root of b square minus 4ac over 2a. After simplifying this, you obtain these two values, minus positive 4a, minus 3. But I think that general quadratic formula is advisable when these coefficients of the quadratic equation are not integers. If they are integers, it's better to try to solve the given quadratic equation with the factorization method. So if this is your question, let us pass it to the next example. The example in B is, again, a degree 3 polynomial is given. G of x is equal to x cubed plus 10x squared minus 24x. Again, I will advise you to find the zeros of a polynomial, or whenever you are trying to find the zeros of a given polynomial, if x is a factor of every term. If x is a factor of every term, don't directly try to find the zeros of the polynomial. Rather, factorize g of x as follows. If you take x out, then you are left with x squared plus 10x minus 24. Now, setting g of x equal to 0, x times x squared plus 10x minus 24 equal to 0. Now use product property here. The product of two numbers is equal to 0 when either of them are equal to 0 or both equal to 0. So you set x is equal to 0, or the expression inside the bracket, x squared plus 10x minus 24 equal to 0. Now x squared plus 10x minus 24 equal to 0. Because the coefficients of this quadratic equation are integers. Now try to find two integers. Their product is minus 24 and their sum is 10. If you are trying to remember this method, then what you do is list the factors of 24. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. From among these factors, if there are two factors of 24, when multiplied together gives negative 24 and obtained a sum of 10, then the middle term will be substituted by those two integers. Now the two integers exist. Who can tell me these two integers? Oh, here I write, therefore no need of waiting for your answers. Negative 2 and 10. Negative 2 times 12, it is equal to negative 24. Negative 2 plus 10, it is negative 2 plus 12, it is equal to 10. So the two numbers satisfying this criteria are minus 2 and positive 12. So the middle term, 10x, is substituted by minus 2x plus 12x. So x squared minus 2x plus 12x minus 24. Take these two and the other two and factorize. The GCF of these two is x. X into x minus 2. And the GCF of 12 and 24 is 12. 12 into x minus 2. X minus 2, x minus 2 is common. So you take out x minus 2, you are left with x plus 12. X minus 2 equal to 0, or x plus 12 equal to 0. Solving these two equations, x is equal to 2 or x is equal to minus 12 is obtained. So we obtain all the zeros of this polynomial. Minus 12, 0, and 2. This is the second way. We have to treat a problem like this. If x is a factor of all the terms in our polynomial, before we go just like how we solved the first example, Rather, it is preferable to factorize and minimize the steps involved in solving this problem. Now let us consider the third example. The third example is h of x is equal to x to the power of 4 plus 2x cubed minus 4x squared minus 7x minus 2 is provided. Again, because the leading coefficient of this polynomial is 1. If this polynomial has any rational zeros, it must be from among the factors of 2, plus or minus 1 or plus or minus 2. Now we don't know whether 1 or 2, minus 1 or minus 2, the zeros of this polynomial. And in this case, all it matters is finding 2 zeros. If you find 2 zeros, then you convert them to a factor. You will take their product. You divide this polynomial to the product of the factors. Then you solve the quotient equal to 0. Then you will have all the possible zeros of this polynomial. That means h of x equal to 0, x to the power of 4 plus 2x cubed minus 4x squared minus 7x minus 2 equal to 0. Because h is a degree 4 polynomial, we must get 2 zeros and then divide h of x by the product of the factors and factorize the quotient obtained. And in this case, because I already checked this example, therefore, if you evaluate it at x is equal to minus 1, it is equal to 0. That means minus 1 is the 0 of h, and x plus 1 is a factor of this polynomial. X plus 1 is a factor of this polynomial. A 0 is changed into a factor by simply subtracting that 0 from x. X minus that number, a given 0 is changed into a factor. So x minus minus 1 is x plus 1. Again, when x is equal to 2, the value of h of x is equal to 0. That means 2 is the 0 of this polynomial. If 2 is the 0 of this polynomial, x minus 2 is the factor of this polynomial. As I told you earlier, all it matters in finding the zeros of a polynomial when its degree is equal to 4 is finding the 2 zeros. You convert them into a factor. Now you divide h of x by the product of x plus 1 and x minus 2. X plus 1 times x minus 2 is equal to x squared minus x minus 2. Because x plus 1 and x minus 2 are both factors of this polynomial. The remainder obtained when h of x is divided by the product of these factors is obviously 0. So to find the remaining zeros of this polynomial, you solve the equation, the quotient equal to 0, after going through long division. So long division results in, I think it hides the divisor, but anyways, when this polynomial is divided by the product of the two, that is x squared minus x minus 2, the quotient x squared plus 3x plus 1 is obtained. But because x squared plus 3x plus 1 equal to 0, even if the coefficients of this polynomial are all integers, it is not possible to find the solutions or the zeros of this polynomial with the factorization method. So the choice left for us is using the general quadratic formula. So the coefficient of x squared, that is a, is 1. The coefficient of x, which is b, it is equal to 3. And the constant term c, it is equal to 1. So x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. b, because it is 3, minus 3 plus or minus b squared against 3 square is 9. Then minus 4 times a times c. Because both a and c are 1, 1 times 1 is 1. 1 times minus 4 is minus 4, 9 minus 4. 9 minus 4 is 5. So minus 3 plus or minus root 5 over 2. X is equal to minus 3 minus root 5 over 2, or x is equal to minus 3 plus root 5 over 2. So all the zeros of this polynomial are therefore -1, -3, minus root 5 over 2, 2, and -3 plus root 5 over 2. These are the 4 zeros of this polynomial. Okay, let us see the next example. Example 2. The height above ground level in meters of a missile launched vertically is given by h of t is equal to -16 t cube plus 100 t, where h represents the height above the ground level in meters and t represents time. At what time is the missile 72 meters above ground level? T is time in seconds. This problem is, I think, not a big deal. It is simple because height ht equal to 72. Then you solve for t. That means indirectly you will find the zeros of the polynomial after taking 72 to the other side. But remember, because t is time in seconds, it can take only positive values. T must be greater than 0. After solving the equation h of t is equal to 72, -16 t cube plus 100 t is equal to 72 is obtained. Then take 72 to the other side in order to write this equation in the standard form. Writing an equation or an inequality in the standard form means one side of the equation or the inequality is equal to 0. So -72, this becomes 0. Now, if you consider the coefficients in this polynomial, -16, 100, and -72. -4 is common for all of them. So let us factorize this as -4 into 4t cube minus 25t plus 18 equal to 0. Now ignore -4 and totally focus on 4t cube minus 25t plus 18. And from among the possible numbers we consider 2. When t is equal to 2, -4 times 2 cubed plus 25 times 2 minus 18. -4 times 2 cubed. 2 cubed is 8, negative 32. 25 times 2 is 15. Then we have -18. -32 minus 18 plus 50, which is equal to 0. Now, because this is a degree 3 polynomial, now all it matters is until we get a 0 of this polynomial. We convert it into a factor, then we divide 4t cube minus 25t plus 18 to t minus 2, then we solve the quotient. That means the quotient, now in this case, I am not going to go the details to how you can divide this by t minus 2. Rather, I will simply tell you the quotient. The quotient is 4t squared plus 8t minus 9, while the remainder is 0. So 4t plus 8t minus 9 equal to 0. So if you try to solve this with a factorization method, you have to find two numbers. Their product is 4 times minus 9, negative 36, and their sum is 8. And these two numbers are not, unfortunately, they are not integers, but they exist. They are irrational, but they exist. So the irrational zeros of a quadratic function, a quadratic equation can be obtained using the general quadratic formula. So A is 4, B is 8, C is minus 9. Now in the general quadratic formula, minus B plus or minus the square root of B square minus 4AC over 2A, we substitute A by 4, B by 8, and C by minus 9. And the result is minus 8 plus or minus B square, that is 8 square is 64, minus 4 times minus 9, it is equal to positive 144. 144 plus 64 is 208. And the denominator is 2 times a, because a is 4, 2 times 4 is 8. So minus 8 plus or minus the square root of 208 over 8 is obtained. Remember, t cannot take negative values because t is time in seconds. So minus 8 plus or minus 208 is 16 times 13. 16 is a perfect number. The square root of 16 is 4. So the square root of 208 is 4, the square root of 13. Now 8, 4, and 8. They can be all divided by 4. So we are left with minus 2 minus root 13 over 2. So after approximating this number to the nearest one digit decimal or to the nearest 1 dp, you obtain negative 2.8. The other irrational number, minus 2 plus root 13 over 2, when approximated to the nearest 1 dp, you obtain 0.8. But because t is time in seconds, we are not going to consider negative 2.8. So the possible values of t are 0.8 and 2. So after 2 seconds or 0.8 second is equal to 8 microseconds. So after 2 seconds or 8 microseconds after it is launched from the ground, the missile will be 72 meters above the ground level. And it is what we are asked to find. So the answers for this question are immediately after 2 seconds or after 8 microseconds after it is launched, this missile will be 72 meters above the ground level. Okay, with this example, we are about to finalize our today's discussion. Before that, I give you these 2 questions to be solved by you. I will wait for a while until you try these 2 examples. Both polynomials are a degree 3 polynomial. So in both cases, all it matters is finding a 0. You convert that 0 into a factor. You divide these polynomials to that given factor. You obtain, if that is a factor, a remainder 0 and a quotient. So by solving the quotient, that is a quadratic equal to 0, you obtain the other zeros if they exist. So by going through this way, find the zeros of these 2 polynomials. At least solve A. It's time for you.
Suggest customer.
እስቲ የቢን ሞክሩት። አይ ቲንክ የቢ ቀለል ይላል። ቢን ሞክሩት። ቢ አረክበት እንደ ይሄን አረክበት Okay, good morning to you. Last Monday, our discussion was on how to find zeros of a polynomial. And we have said that to find the zero or zeros of a given polynomial, we solve the equation. For example, if the given polynomial is f of x is equal to 0. And I told you that if the leading coefficient of a polynomial, is 1, we totally list the factors of the constant term. And if that polynomial has a rational 0, then it must be among from those factors of the constant term. But actually, a given polynomial may have an irrational or rational 0, because the set of real number is the union of these two sets. Then we have two theorems, rational root test theorem and location theorem, which are greatly helping us in finding the zeros of a polynomial. The first one, rational zero, it is helpful in finding the rational zeros of a polynomial. And the second theorem, location theorem, it is helpful in locating where the irrational zeros of a polynomial appear. Because if you remember from your grade 9 mathematics lesson, an irrational number has no specific and unique value, rather it has an approximate value. So what we do is we locate that irrational number between consecutive integers. So in this case, we locate the zeros of a polynomial between consecutive integers. But it has a separate discussion. We will try to see this after you return back to normal class starting from Monday. So today we are going to see zeros and their multiplicities. But you have to note this point, a polynomial function cannot have more zeros than its degree. The maximum possible number of zeros a polynomial can have is always equal to its degree. For example, a polynomial whose degree is 3 can have 3 different zeros at maximum, or it can have 2, 1, 0. All these are possible. But the maximum possible number of zeros a polynomial can have is equal to its degree. This is an important point. So having said this, let us turn our focus to our today's topic, that is multiplicity. Multiplicity, it is simply, or to understand this very simply, if you prime factorize this composite number 12, it is to the power of 2 times 3. 3 is the power of 1. Now, after prime factorizing a number, then consider the power of these prime factors. The power of 2 is 2, the power of 3 is 1. Now, these two numbers, 2 and 1, in polynomial, after factorizing a polynomial or expressing a polynomial as a product of its factors, then the power of a given factor or the power of factors, they indicate how many times a given factor appears as a factor of a given polynomial, and it is called the multiplicity of that factor. So for example, if x minus c the power of k is a factor of f of x, where k is a natural number greater than or equal to 1, then if x minus c the power of k is a factor of f of x, but x minus c the power of k plus 1, x minus c the power of k plus 1 is not, then c is said to be a zero of multiplicity k of f. Actually, how this definition is used to determine the multiplicity of a factor is, we use polynomial long division. How we use that? Let us see it with examples. The first example is, in each of the following, the indicated number is a zero of the polynomial function f of x. Determine the multiplicity of this zero. First, you are given with a zero, so convert it into a factor. So use the factor theorem. According to the factor theorem, if f of c is equal to 0, then x minus c is the factor of that polynomial, or x minus c is the factor of that polynomial, c is the zero of that polynomial. So when 2 is converted into a factor, it is x minus 2. 2 is a 0 for f of x, but x minus 2 is the factor of f of x. Now, x minus 2 now, according to definition 1.3, you have to increase the power of x minus 2 by 1. That means x minus 2, the power of 1 is a factor of f of x. It is given. So we do x minus 2 the power of 1 plus 1. That is 2. x minus 2 the whole square. Take x minus 2 the whole square. X minus 2 the whole square is x square minus 4x plus 4. You divide f of x by x minus 2 the whole square, or x square minus 4x plus 4, and you observe the remainder. If the remainder obtained when f of x is divided by x square minus 4x plus 4 is 0, then we factorize the quotient if it is not a linear polynomial. Because in this case, the polynomial is a degree 4 polynomial, and the divisor is a degree 2 polynomial. Obviously, the quotient is a degree 2 polynomial. So a degree 2 polynomial or quadratic, we factorize it. Now, x is the power of 4 minus 5x cubed, 6x squared plus 4x minus 8 divided by x squared minus 4x plus 4. That is the divisor, which is obtained by increasing the power of x minus 2, which is a factor of f of x, by 1. So we obtain the quotient x squared minus x minus 2, and the remainder 0. Now, because the remainder is 0, we have to factorize the quotient x squared minus x minus 2. So to factorize x squared minus x minus 2, we either use the factorization method or the general quadratic formula. So because the remainder is 0, if the remainder was not 0, we stop this process and we determine that the multiplicity of x minus 2 as a factor of f of x is 1, because f of x divided by x minus 2 the whole square, its remainder is not 0. Okay, x squared minus 4x, I mean the quotient x squared minus x minus 2. Try to factorize this one. To factorize this, find the two integers, their product is minus 2 and their sum is minus 1. These two integers exist. Their product is minus 2 and their sum is minus 1. These two integers are minus 2 and positive 1. Because minus 2 times 1 is minus 2, minus 2 plus 1 is minus 1. So the middle term in this quadratic expression is substituted by minus 2x plus x. X squared minus 2x plus x minus 2. Now factorize these two first and the last two later. So x squared minus 2x, x is the GCF of these two terms. So x into x minus 2. And this one is x minus 2. X and 2 are relatively prime. So 1 plus 1 times x minus 2. Here we have x minus 2, x minus 2. So we take out x minus 2. So we are left with x plus 1. So in factorized form, x squared minus x minus 2 is equal to x minus 2 times x plus 1. Now we have here x minus 2 the whole square as a factor of f of x. And we have two more factors of f of x, x minus 2 and x plus 1. So f of x can be obtained from the product of its factors as x minus 2 times x minus 2 the whole square times x plus 1. Now x minus 2 the whole square times x minus 2, it is x minus 2 cubed. X minus 2 cubed, x plus 1. The final step in determining the multiplicity of a factor of a given polynomial is, after you completely factorize a given polynomial if it is possible, then you consider the power of that factor. In this case, we are asked to find the multiplicity of 2. So the multiplicity of 2 is 3, because the exponent or the power of x minus 2 in f of x is equal to x minus 2, the power of 3 is equal, times x plus 1 is 3. So the multiplicity of this 0 or the multiplicity of x minus 2 is 3. If you have any question before we pass to the next example, you can forward it. Okay, if no problem, let us consider the second example. The second example is given a degree 3 polynomial 4x cubed minus 8x squared minus 3x plus 9. It is given that 3 over 2 is 0. First, convert this 0 to a factor. Simply x minus 3 over 2 or 2x minus 3. The same result can be obtained from this. X minus 3 over 2 or 2x minus 3 is a factor of this polynomial. As we did for the previous example, we first add 1 to the power of this one, x minus 3 over 2 to the power of 1. It is a factor of this polynomial and it is given. It is not something we brought by going through with some calculation, rather it is given. So convert this into a factor, then add 1 to the power of this factor, that is 1 plus 1, it is equal to 2. So x minus 3 over 2 to the power of 2, write this in its expanded form. So the result is x squared minus 3x plus 9 over 4. Now we divide f of x by x squared minus 3x plus 9 over 4 and observe the remainder. If the remainder is 0, we factorize the quotient if the quotient is not a linear or degree 1 polynomial. But in this case, because this polynomial is a degree 3 polynomial, the quotient obtained after dividing this degree 3 polynomial by a divisor whose degree is equal to 2 is linear. What matters is therefore the remainder obtained. So the polynomial 4x cubed minus 8x squared minus 3x plus 9 divided by x squared minus 3x plus 9 over 4. The quotient is 4x plus 4. Now write this polynomial f of x as a product of its factors. 4 times x plus 1 times x minus 3 over 2 the whole square. This is f of x. F of x is equal to 4 times x plus 1 times x minus 3 over 2 the whole square. Now, because we are asked to determine the multiplicity of 3 over 2 or the multiplicity of the factor x minus 3 over 2, this question is the same as what is the power of x minus 3 over 2 in the final polynomial f of x, when after writing f of x as a product of its factor, what is the power or exponent of x minus 3 over 2? And as you can see, the power or exponent of x minus 3 over 2 is 2. The multiplicity of 3 over 2 is 2. We are asked to find its multiplicity, and the multiplicity of this is 2. Then C. Again, in this case, we are given with 1, 0 of the polynomial 4 over 3, and a degree 3 polynomial f of x is given, and we are asked to find its multiplicity. Again, this question is the same as factorize f of x and what is the power corresponding to 4 over 3. 4 over 3 as a factor, it is either x minus 4 over 3 or when converted into a factor, it is equal to 3x minus 4. So now add 1 to the exponent of x minus 4 over 3. So you have x minus 4 over 3, the whole square. Then write that in its expanded form and use long division. And divide f of x by x minus 4 over 3, the whole square. Then observe the remainder. So x minus 4 over 3 the whole square is 9x squared minus 24x plus 16. So dividing 3x cubed plus 2x squared minus 17x plus 12 to 9x squared minus 24x plus 16. Long division results. The quotient is 1 over 3x plus 10 over 9, and the remainder is 13 over 3x minus 52 over 9. Check it for yourself. Divide f of x by 9x squared minus 24x plus 16. The remainder is 13 over 3 13 over 3x minus 52 over 9. So the remainder is 0. So the multiplicity of 4 over 3 as a 0 of this polynomial is only 1. The multiplicity of 4 over 3 is different from 1 if a remainder of 0 was obtained, and after factorizing the quotient, it may appear as a 0 of this polynomial. So after writing as a at the final stage, we write f of x as a product of its factor, and then we observe the power of that 0 or that factor. So because of this, 4 over 3, which is the 0 of f of x, its multiplicity is 1. Example number 2, find the 0 or zeros of f of x and determine its multiplicity if f of x is equal to 2x the power of 4 minus 12x cubed plus 21x squared minus 18x plus 27. Actually, because I already see this problem before coming here. So what we do is, if we were using the rational root test theorem, we write the factors of 27, we write the factors of 2, then we take the factors of the constant term divided by the factors of the leading coefficient. Then from among those numbers, f can have its 0. But in this case, the first 0 of f can be obtained by solving f of x equal to 0. First, f of 3. f of 3 is equal to 0 because 2x the power of 4, 2 times 3 the power of 4, minus 12x cubed, because x is equal to 3, 3 the power of 3, plus 21 times x squared, because x is 3, 21 times 3 squared, minus 18 times 3 plus 27. 3 the power of 4 is 81. 81 times 2 is 162. And in this case, 3 cube is 27. 27 times 12 is 324. 3 square is 9. 9 times 21 is 189. And 18 times 3 is 54, and it is negative. So now add the positive numbers together and the negative numbers together. 162, 189, and 27. Their sum is equal to 378. Negative 324 and negative 54. It is equal to negative 378. So 378 minus 378 is equal to 0. Oh, it's good. We have got 1 0 of this polynomial. So to find the other zeros of this polynomial, let us apply multiplicity. Increase the power of x minus 3 by 1. X minus 3 is the power of 2. It is equal to x squared minus 6 plus 9. Divide f of x to x the power of 4 minus 12x cubed, 21x squared, minus 18x plus 27 by x squared minus 6x plus 9. Then you observe the remainder. If the remainder is exactly equal to 0, then the next step is factorize the quotient. Now 2x the power of 4 minus 12x cubed plus 21x squared minus 18x plus 27 divided by x squared minus 6x plus 9. A quotient of 2x squared plus 3 and a remainder of 0 is obtained. That means at least up to this stage, f of x is equal to x minus 3 the whole square times 2x squared plus 3. But this is a quadratic having only 2 terms, and I told you a number of times that if a quadratic expression has only 2 terms, and if its 2 terms are joined by this positive sign or with the plus sign, it is not factorizable. 2x squared plus 3 is not factorizable. That means f of x is equal to x minus 3 the whole square times 2x squared plus 3. So f of x is equal to 2x squared plus 3 times x minus 3 the whole square. So the only zero of f is 3 with multiplicity 2. If 2x squared plus 3 was factorizable, then we may have another 0 with multiplicity 2 or 1, because this is a degree 2 polynomial. When it is factorized, it is equal to a single factor, the whole squared, or the product of two linear factors. So if 2x squared plus 3 was factorizable, then the possibilities may be we may have two different factors with multiplicity 1, or a single factor with multiplicity 2. But both are simply possibilities, because 2x squared plus 3 is not factorizable. The only zero of this polynomial is 3, and its multiplicity is 2. Now, if you have any question, you can forward it. If not, it's time for you to try these two questions. Find the zero or zeros of the following polynomials and determine its multiplicity. ሮብሰን እየሞከራችሁ ነው እ አልተሰማኝም። የከበዳችሁ ነገር ካለ ነገሩኝ መጀመሪያ ወይስ ኦኬ ሞክሩትና ቆይ እንነጋገራለን። እንግዲህ መልሱን ልንገራችሁ። ከዚህ በላይ መጠበቅ ብዙም አይቻልም። ስለዚህ for the first polynomial 1 and minus 1 are its zeros. So if you start from 1 is a zero of this polynomial, because if you see the first polynomial, its coefficients are all 1. In this polynomial expression, the coefficients of all the terms are 1, minus 1, minus 1, 1. So if you substitute x by 1, 1 minus 1 is 0, minus 1 plus 1 is 0. So you divide f of x by x minus 1 the whole square. Then the quotient, the remainder is 0, and the quotient obtained is x plus 1. So you write f of x as x plus 1 times x minus 1 the whole square. Therefore, the zeros of this polynomial are minus 1 and 1, minus 1 with multiplicity 2. I mean 1 with multiplicity 2. The multiplicity of minus 1 is only 1 because its exponent is 1. But the multiplicity of 1 is 2. X plus 1 is a factor of this polynomial, means minus 1 is, it is 0. X minus 1, the whole square, is a factor of this polynomial, 1 with multiplicity 2. Multiplicity 2. So the zeros of this polynomial are minus 1 and 1, where the multiplicity of 1 is 2. For the second polynomial, x cubed plus 3x squared plus 3x plus 1. Again, if you observe simply, the coefficients in this polynomial expression, 1, we have 1, 3, we have 3. So if there is a chance for one of these two ones to be negative, and from these two threes, one, if there is a possibility for one of them to be negative, then obviously we obtain a 0. So if you make the value of x minus 1, minus 1 cube is minus 1. So minus 1 plus 1 is 0. Here minus 1 square is positive 1. So it is 3. But 3 times minus 1 is minus 3. Minus 3 plus 3 is 0. Again, minus 1 is the 0 of this polynomial, means x plus 1 is its factor. So as we did for all the examples we consider today, divide f of x by x plus 1 the whole square. Obviously, this is a degree 2 polynomial, I mean a degree 3 polynomial, and the divisor is a degree 2 polynomial. A linear polynomial will be obtained. Divide f of x by x plus 1 the whole square, whose expanded form is x squared plus 2x plus 1. Now, the quotient obtained when f of x is divided by x squared plus 2x plus 1 is x plus 1, and its remainder is 0. That means f of x is equal to x plus 1 the power of 3. So this polynomial has only one 0 with multiplicity 3. Minus 1 is the 0 of this polynomial with multiplicity 3. This is all I have for today. So see you next week in person. But the first 4 weeks are dedicated for revising some of the key points from your grade 9 mathematics. Then after those 4 weeks, we will come back again and revise some of the key points we raised in our discussion the last 4 or 3 weeks. Then we will continue like this. Thank you for listening. So see you next week on Tuesday. Well, እንግዲህ Okay, good afternoon to you.
Good afternoon, Mister.
Waiting room ላይ ምንም ሰው የለም። Okay, in our discussion today, we'll try to see additional examples on how we can use the rational root test theorem to find the rational zeros of a polynomial. In our previous meeting, that is last Friday, we have seen the location theorem and the rational root test theorem, and we have said that the location theorem is used to locate the irrational zeros of a polynomial between consecutive integers where the given polynomial changes its sign from positive to negative or from negative to positive. And this is possible, that means locating the irrational zeros of a polynomial is possible by constructing a table of values. Most often, we consider the possible values of x as -2, -1, 0, 1, and 2, or these 5 integers. But if there is a need, we may consider values like 3, 4, -3, -4, in case if there is a need. But most often, by evaluating the given polynomial at these 5 integers, we can observe and we can determine where the irrational zeros of a given polynomial are located. The second theorem is actually the rational root test theorem, and it is basically used to find the rational zeros of a polynomial if they exist. And the main idea behind this theorem is that first, make sure all the coefficients of the polynomial are integers, because this theorem can be used only if all the coefficients of the polynomial are integers. If they are not integers, then we must do some calculation to make the coefficients of the given polynomial all integers. In this case, in the examples A, B, and C, because the coefficients of the polynomials are all integers, so there is no need to make some kind of calculation. Rather, we have to focus on the constant term and the leading coefficient. List the factors of the constant term, and it is P. List the factors of the leading coefficient, it is Q. So for the first one, P is 3, so the factors of 3 are plus or minus 1 and plus or minus 3. Q, the factors of Q, that is 12, are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Now, we are interested in the factors of P over Q. We form the rational number whose numerator is P, whose denominator is Q. This is the complete list of possible rational zeros of this polynomial. So plus or minus 1, don't forget to put this one. Then make the numerator of this fraction 1 and its denominator 1, 2, 3, 4, 6, and 12. So we have plus or minus 1, plus or minus 1 over 2, plus or minus 1 over 3, plus or minus 1 over 4, plus or minus 1 over 6, plus or minus 1 over 12. Then make the numerator of this fraction P over Q3 and its denominator 1, 2, 3, 4, 5, 6. These 12 numbers. So by putting the plus or minus sign, then 3 over 1, it is equal to plus or minus 6. 3 over 2, plus or minus 3 over 2. 3 over 3, it is plus or minus 1, already recorded. Then 3 over 4, plus or minus 3 over 4. Plus or minus 3 over 6. 3 over 6 is 1 over 2, already recorded. 3 over 12, it is 1 over 4, already recorded. Therefore, if this polynomial P, which is a degree 3 polynomial, and it can have at maximum 3 different zeros, and if these rational zeros exist, then it must be from among these 1, 2, 3, 4, 5, 6, 7, 8, 9. from among these 18 list of rational numbers. So we have now narrowed down our search. That means rather than thinking to solve this, the zeros of this polynomial from the set of real number, we have to focus on this list of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. From among these 18 numbers, 1, 2, or 3 of them will make at maximum this polynomial equal to 0. Now the next thing is evaluate this polynomial at these 18 numbers. We may not necessarily to evaluate this polynomial at all the 18 numbers. Rather, we can start from the simplest numbers. These simplest numbers are plus or minus 1. Okay, so when x is equal to 1, evaluating the given polynomial at x is equal to 1 means simply add the coefficients of this polynomial. 7 minus 7 minus 8 is minus 15. 12 plus 3 is 15. 15 minus 15 is 0. Obviously, x is equal to 1 is a 0 of this polynomial, because 12 times 1 cube minus 7 times 1 square minus 8 times 1 plus 3, which is equal to 12 plus 3 minus 8 minus 7, it is equal to 0. Now we obtain 1 0 of this polynomial. Then we have to find the other zeros if they exist. Actually, they exist. And the other rational zero of this polynomial is x is equal to 1 over 3. When x is equal to 1 over 3, p of 1 over 3 is equal to 12 times x cubed. Because x is substituted by 1 over 3, 12 times 1 over 3 cubed minus 7 times 1 over 3 squared minus 8 times 1. So 1 over 3 cubed means 1 over 27. 1 over 3 square means 1 over 9. Then 12 times 1 over 27. By 3, it is equal to 4. By 3, it is equal to 9. So the simplest form of this is 4 over 9. Then we have minus 7 over 9, minus 8 over 3, plus 3. So by making the denominator of this 9, and it is possible by multiplying the numerator and the denominator by 3. So we have 4 minus 7 minus 24. We have minus 31. Minus 31 over 9 plus 3. And this is equal to 31 over 9 minus 31 over 9, or simply 4 over 9 times 4 over 9 plus 3. 9 times 3 is 27. 27 plus 4 is 31. 31 over 9. Minus 7 over 9 minus 8 over 3. If you multiply this by 3 over 3, this is minus 24. Minus 24 minus 7 is minus 31. So we have 31 over 9 minus 31 over 9, which is equal to 0. So we have a second zero of this polynomial. Obviously, the third rational zero of this polynomial exists, and it is equal to minus 3 over 4. If you evaluate this polynomial at x is equal to minus 3 over 4, the result is 0. So we can write P of x in factorized form as 3x minus 1 or x plus 3 times x minus 1. Because by the factor theorem, if x is equal to minus 3 over 4 is a zero of this polynomial, then x plus 3 over 4 or 4x plus 3 is a factor of this polynomial. So we have 4x plus 3. X is equal to 1 over 3 is a zero of this polynomial. Again, by the factor theorem, x minus 1 over 3 or 3x minus 1. It is a factor of this polynomial. Already, we have x is equal to minus 1 as a factor of this polynomial. So P of x is equal to 3x minus 1 times 4x plus 3 times x minus 1 and minus 3 over 4, 1 over 3, and 1 are its zeros. Okay, the second example is we have a second polynomial. Again, it is a degree 3 polynomial, 4x cubed plus 8x squared plus 5x plus 1. Now, the leading coefficient of this polynomial is not 1. Its constant term is 1, and the factors of 1 are plus or minus 1, and the factors of 4 are plus or minus 1, plus or minus 2, and plus or minus 4. So the factors of P in this case is 1, it is plus or minus 1. The factors of Q, that is in this case is 4, are plus or minus 1, plus or minus 2, and plus or minus 4. Now we are interested in the factors of P over Q. And they are obtained by making the numerator of the rational number 1 and its denominator one of the 6 numbers, 1, 2, 4, plus or minus 1, plus or minus 2, plus or minus 1. So by putting the plus or minus sign before the numbers, 1 over 1 is 1, so plus or minus 1. Then 1 over 2, plus or minus 1 over 2. Then 1 over 4. These 6 numbers. So if this polynomial P has a rational 0, it must be from among these 6 numbers. There is no other number which is element of the set of real number, and it is rational, that can make this polynomial equal to 0 other than these 6 numbers plus or minus 1, plus or minus 1 over 2, and plus or minus 1 over 4. So at maximum, our effort of determining the rational zeros of this polynomial involves making calculation at 6 different times. Evaluating P at minus 1, at 1, evaluating P at minus 1 over 2, 1 over 2, and evaluating finally P at 1 over 4 and minus 1 over 4. As we have said earlier, evaluating the given polynomial at plus or minus 1 is a very simple task. So always you have to start from these numbers whenever you try to determine the rational zeros of the polynomial. Now P of x is 4x cubed. It is 4x cubed, 8x squared plus 5x plus 1. So P of minus 1 is 4 times minus 1 over 3 plus 8 times minus 1 the whole square plus 5 times minus 1 plus 1. Minus 1 cube is minus 1, minus 1 times 4 is minus 4. Minus 1 square is 1, 1 times 8 is 8. 5 times minus 1 is minus 5. Then we have positive 1. 1 plus 8 is 9. Minus 4 minus 5 is minus 9. Minus 9 plus 9 is equal to 0. We have obtained one rational zero of this polynomial. Then by evaluating this polynomial at x is equal to minus 1 over 2. P of minus 1 over 2 is equal to 4 times minus 1 over 2 cube, 8 times minus 1 over 2 the whole square, 5 times minus 1 over 2 plus 1. So minus 1 over 2 cube is minus 1 over 8. Oh. So minus 1 over 8 times 4, 8 times 1 over 4, minus 5 over 2 plus 1. 4 times minus 1 over 8, it is equal to minus 1 over 2. 8 times 1 over 4, it is 1 over 2. Then we have minus 5 over 2 plus 1. Minus 1 over 2 minus 5 over 2. Minus 1 minus 5 is minus 6. Minus 6 over 2 is minus 3. We have here 1 over 2 plus 1. 2 times 1 is 2. 2 plus 1 is 3. So it is equal to 3 over 2. 3 over 2 minus 3 over 2. It is equal to 0. And P of x is equal to, if you try to express P as a product of its factor, it is equal to x plus 1 times 2x plus 1, the whole square. So the only zeros of this polynomial are minus 1 and minus 1 over 2, where the multiplicity of minus 1 over 2 is 2. That is the reason why this polynomial, which is a degree 3 polynomial, has only two zeros, minus 1 and minus 1 over 2. Actually, for this polynomial, if we talk about the possibility at the start of solving this problem, one rational number can make this polynomial 0, but its multiplicity may be 3. So when we are talking about the possibilities are this polynomial may have only one rational 0 with multiplicity 3. It may have 3 different rational zeros, each with multiplicity 1, or from among the rational zeros of this polynomial, one of them may have a multiplicity 2, the other 1. These are all the possibilities, and what happens to the zeros of this polynomial is minus 1 has a multiplicity of 1, and minus 1 over 2 has a multiplicity 2. For the third example, P of x is equal to 20x squared plus 27x minus 14. Actually, we can solve this, or we can find the zeros of this polynomial in two different ways. One is, because it is a degree 2 polynomial, we can approach this problem, or we can treat this problem using the general quadratic formula, or we can use the content of the rational root test theorem. Because all its coefficients are integers, list the factors of the constant term 14, list the factors of the leading coefficient 20, then list the factors of P over Q in its simplest form. Then from among those numbers, we substitute x by those numbers, and we take the numbers that makes this polynomial equal to 0 as the rational zeros of this polynomial. But I think this one is easy if you treat this problem using the general quadratic formula. 20x squared plus 27x minus 14. The general quadratic formula states that if you have the quadratic equation ax squared plus bx plus c equal to 0, for a different from 0, x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. Then a is the coefficient of x squared, b is the coefficient of x, and everything that is left, it will be c. So a is 20, b is 27, c is negative 14. So it may be good to find the rational zero or zeros of this degree 2 polynomial by treating it as a quadratic equation. 20x squared plus 27x minus 14 equal to 0. A20, B27, C minus 14. So in this quadratic formula, we substitute A by 20, B by 27, C by minus 14. So the result is negative B. Because B is a positive number, negative 27 plus or minus the square root of 27 squared plus, this is plus because we have minus 4, and here we have C negative 14. Negative times negative is positive. So 14 times 20 times 14 over 2a, 2 times 20. Now minus 27, 27 squared is 729. 4 times 20 times 14 is 1120. And the sum of these two numbers is equal to 729 plus 1120. It is equal to 1849, and its square root is equal to 43. So x is equal to minus 27 plus or minus 43 over 40. Now, there are two possible values of x. One is negative 27 minus 43 over 40, and the other is minus 27 plus 43 over 40. Negative 27 minus 43 is minus 70. So we have minus 70 over 40 in its simplest form, minus 7 over 4. Minus 27 plus 40, it is equal to 16. 16 over 40, it is equal to 2 over 5. That means the rational zeros of this degree 2 polynomial are minus 7 over 4 and 2 over 5. If you try to solve this problem, you came up with the same answers. The only rational numbers from among the list of factors of P over Q that does make this polynomial equal to 0 are minus 7 over 4 and 2 over 5. So by using the rational root test theorem, we have determined all the rational zeros of this polynomial. If you have any question, you can forward it or we can pass it to the next example. Okay, example 2. For the polynomial f of x is equal to x plus 6 times 3 minus x the whole square. What are the zeros of f? Determine the multiplicity of the zeros of f. What is a2? The coefficient of x squared. What is the sign of the constant term of f? What is the leading coefficient of f? Already, we are lucky because f of x is given as a product of its prime factors. F of x is equal to x plus 6 times 3 minus x the whole square. So what are the zeros of f? X plus 6 equal to 0 and 3 minus x equal to 0. Solve these two equations. X plus 6 equal to 0 or 3 minus x equal to 0. X plus 6 equal to 0, the result is x is equal to minus 6. 3 minus x equal to 0, 3 is equal to x or x is equal to 3. So minus 6 and 3 are the zeros of this polynomial. Determine the multiplicity of the zeros of f. As we have seen the previous week, multiplicity of a zero or a factor in a polynomial means the exponent or power of a factor when the polynomial is written in factorized form. So the exponent or the power of x plus 6 in this polynomial expression is 1, while 3 minus x is 2. Therefore, the multiplicity of minus 6 is 1. The multiplicity of 3 is 2. The multiplicity of minus 6 is 1, and that of 3 is 2. See, we are asked to find a2, the coefficient of x squared. So in order to determine a2, the coefficient of x squared, write this polynomial in its expanded form. X plus 6 times 3 minus x is the whole square. And 3 minus x is the whole square means 9 minus 6x plus x squared. So the product of x plus 6 and 9 minus 6x plus x squared is, it is equal to x cubed minus 5x squared plus 3x plus 9. So from this, the coefficient of x squared is minus 5. That means a2 is negative 5. See, a2, the coefficient of x squared is equal to minus 5. And D, we are asked to determine what? The sign of the constant term of f. As you can see, the constant term of this is positive 9. So the constant term of f is a positive number because we are asked its sign. What is the sign of the constant term of f? E, what is the leading coefficient of f? Because this polynomial is a degree 3 polynomial, what is the coefficient of x cubed? It means the coefficient of x cubed, as you can see, it is 1. So the leading coefficient of this polynomial is 1. Okay, the next example. Example 3. Write only all the possible list of rational zeros of the polynomial. In this case, We are not asked to find the rational zeros of the polynomial, but the possible list of rational zeros of the polynomial. My question is, list the factors of P over Q. But when we think of applying the rational root test theorem to solve this problem, the coefficients of this polynomial are not integers. For example, the coefficient of x cube is 7 over 6. The coefficient of x square is minus 7 over 3. The coefficient of x is minus 5 over 2. Necessarily, the coefficient of f of x all must not be rationals. If one of the coefficients is rational, then we have to make some calculation in order to make all the coefficients of the polynomial integers. So in this case, please very carefully observe the denominators. 6, 3, 2. What is the least common multiple of 6, 3, and 2? What is the least common multiple of 6, 3, and 2? It is a very simple question. What is the least common multiple of 6, 3, and 2? I am telling you the calculation, the simple calculation we need to go through to make the coefficients of all the coefficients of this polynomial integers. The answer is 6. The reason is because 6 is the larger of these three numbers, and because 6 is divisible by 3, 6 is divisible by 2, and 6 is divisible by itself. So the least common multiple of all these three numbers is 6. So take 1 over 6 as a common factor of all the terms of this polynomial. So we have f of x is equal to 1 over 6. So when we are multiplying 1 over 6 with a term that contains x to the power of 4, the result must be x to the power of 4. So it is equal to 6x to the power of 4, since 1 over 6 times 6x to the power of 4 is equal to x to the power of 4. Next, if you take 1 over 6, then we have 7x cubed. If you take 1 over 6, then this must be minus 14 in order to get minus 7 over 3x squared. So minus 14x squared. And here we have 2. And here we have 1 over 6. So multiply this by 3. So we have negative 15x. And this one is 24, because 24 over 6 is equal to 4. Now we have to focus on the polynomial expression inside this bracket. And here we have the constant term 24, that is P, and the leading coefficient 6. So P is 24, Q is 6. The factors of 24 or the factors of P are therefore plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. In the constant term Q, its factors are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now the factors of P over Q. We can simply form P over Q by taking one of these numbers as a numerator and all the factors of Q as denominator. By putting this plus or minus sign before the numbers, we can list plus or minus 1 over 1 is 1, so plus or minus 1. Then 1 over 2, plus or minus 1 over 2, 1 over 3, plus or minus 1 over 3, 1 over 6, plus or minus 1 over 6. Then consider the factors of P over Q, whose numerator is 2. So plus or minus 2 over 1 is plus or minus 2. 2 over 2 is 1, so already mentioned. 2 over 3, plus or minus 2 over 3. Then 2 over 6. 2 over 6 in its simplest form is 1 over 3. So we did already mention. So no need of writing or repeating this rational number. So next, list the factors of P over Q whose numerator is 3. So plus or minus 3 over 1. It is plus or minus 3. Then we have 3 over 2. Plus or minus 3 over 2. 3 over 3, it is 1. So plus or minus 1 is already mentioned. Plus or minus 3 over 6. 3 over 6 is 1 over 2. It is already mentioned. So consider the factors of P over Q whose numerator is 4. Then 4 over 1 is 4, so plus or minus 4. 4 over 2, it is 2, already mentioned. 4 over 3, we didn't mention it so far, so plus or minus 4 over 3. 4 over 6 in its simplest form, 2 over 3. It is already mentioned. So pass to the next number and consider the factors of P over Q whose numerators are 6. 6 over 1 is 6, so plus or minus 6. 6 over 2 is 3. 6 over 3 is 2. 6 over 6 is 1. All are mentioned, so no need of repeating them. So consider the factors of P over Q whose numerator is 8. Plus or minus 8 over 1, it is 8. 8 over 2, it is 4. 8 over 3, it is not yet mentioned, so plus or minus 8 over 3. 8 over 6 in its simplest form is 4 over 3, and we did already mentioned it, no need of repeating. So pass it to the next factor of P over Q whose numerators are 12. Plus or minus 12 over 1, it is 12. 12 over 2, 6. 12 over 3, 4. 12 over 6, 2, which are all mentioned except plus or minus 12. So plus or minus 12. Finally, we will list the factors of P over Q whose numerators are 24. So plus or minus 24 over 1, it is 24. So we will mention it because so far it is not mentioned. 24 over 2 is 12. 24 over 3 is 8. 24 over 6 is 4. All are mentioned. So the factors of P over Q are plus or minus 1, plus or minus 1 over 2, plus or minus 1 over 3, plus or minus 1 over 6, plus or minus 2, or this list of numbers which you are seeing on your screens. If you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if this degree 4 polynomial has any rational zero, it must be from among these 30 different rational numbers. But in this case, we are not asked to find the rational zero, rather we list or list all the possible rational zeros of this polynomial whose coefficients were not integers. First we make the coefficients of this polynomial or integers. The next one is we list the factors of the constant term. We list the factors of the leading coefficient. Then by making the factors of the constant term numerator and the factors of the leading coefficient denominator, we came up with this list of 30 different numbers. So these are the possible rational, the list of the possible rational zeros of this polynomial. Okay, we did solve example number 3. I think it is time for you to solve these two questions. Find all the rational zeros of these two polynomials. Please very quickly solve or find the rational zeros of these two polynomials. Robs,
Yes.
እየሞከራችሁ ነው? ሞክር ኑሐሚን ወጣች? ጥያቄ ስሩ ሲባሉ ላጥላት እያሉ ወጡ። 9 የትምህርት ሚኒስቴር ምናምን እዚህም ሲመጣ ነበር። ዳንኤል እውነት Where were you? በቃ ዝግጅት ሊመጣል ይጠልቁልኝ በቃ ችግር የለም እሷም ትምጣ እሺ እሺ ይሄስ ይሄንን እሺ
Sir,
yes
the first one has only one rational zero, which is -3.
-3 only okay no it has two more rational zeros already one of them is given x is equal to 1 f of x is given us x minus 1 times x times x plus 1 plus 2x. So you should focus on factorizing this polynomial which is given inside this bracket. So you will have two rational zeros. One of them is x minus 3. What is the other zero? Please focus on the expression inside the second bracket, x times x plus 1 plus 2x. First simplify, then factorize. Okay. አቤት
መሞከር ቻል
እሺ
የመጀመሪያው -1 -3 እና 1
የመጀመሪያው 1 ኦሬዲ ተሰጥቷል ሌላኛው ማን ያልከኝ በፋክተራይዝድ ፎርም ሲጻፉ ይታያል አይደል እዚህ ስክሪኑ ላይ x - 1 ታይምስ ይሄ ፋክተራይዝ ሲደረግ x ታይምስ x + 3 ነው የሚመጣው ስለዚህ በፋክተራይዝድ ፎርም ውስጥ ጽፈው x ታይምስ x - 1 ታይምስ x + 3 ነው ምክንያቱም ጉዳያችን ያለው እዚህ ላይ ነው አይደል x ታይምስ x x ስኩዌር x ታይምስ 1 x ይመጣል x + 2x 3x ይመጣል ስለዚህ x ስኩዌር + 3x ቀረ ማለት ነው x ነው ወደ ውጭ ካወጣት x ታይምስ x + 3 ቀረ ስለዚህ የዚህ ፖሊኖሚያል ዜሮዎች ራሱ 0 1 እና -3 ናቸው ማለት ነው ወደ ሁለተኛው ጥያቄ ይሁን ሁለተኛውም ጥያቄ እስካሁን እንዳየናቸው ፖሊኖሚያሎች ሊዲንግ ኮኤፊሽንቱ ሌላ ቁጥር ስላልሆነ ይሄ ፖሊኖሚያል ራሽናል ዜሮዎች ካሉት ራሽናል ዜሮዎቹ የ10 ፋክተር የሚሆኑት ቁጥሮች ውስጥ ነው ግን የትኞቹ ቁጥሮች ናቸው እነኚህ ቁጥሮች ፈልጓቸው First list the factors of 10 አንዱ 0 በቀላሉ ፊት ለፊት የሚገኝ ነው 1 ለምሳሌ ቢከቱበት 1 -4 -7 10 ሆነ 1 + 10 11 ነው -4 -7 -11 ነው 11 -11 0 ነው ስለዚህ ሁለቱን ሌሎቹ ራሽናል ዜሮዎች ፈልጉ ማለት ነው Okay, we have we are running out of time. So let me tell you the answers. And this Friday, we are going to start how we can sketch the graph of a polynomial function. Next week, I will try to send you a video on how we can sketch the graph of a polynomial, because I don't think it is everything, we can see everything in this Zoom class. So it's preferable to send a video showing the steps, all the steps involved in sketching the graph of a polynomial function. But anyways, we will start to see the topic this Friday. But for this question, the rational zeros of this polynomial, because f of x as a product of its factors is equal to x minus 1 times x minus 5 times x plus 2, the rational zeros of this polynomial are 1, 5, and minus 2. All are factors of the constant term 10. So the rational zeros of this polynomial are 1, 5, and minus 2. So with this, we come to our today's discussion. See you on Friday.